Perfect. Great answer. If you have a liquid and you give it energy, it takes that energy, breaks the forces of attraction, right? Because liquid particles are close together, but they're moving around. You give it energy, it takes that energy and uses it to break free of those forces, forming a gas. Very good. So if you give a solid energy, it won't break forces. What does it do? Right. So they're vibrating, right? They're not really moving, but then they start moving if you give it energy. So they're not breaking forces. What are they doing? They're just weakening the forces, right? So they're weakening them so they can move. And then what about removing energy? If a gas cools down by getting rid of energy, what does it turn into? If you have a gas or a vapor and it loses energy, what does it turn into? Liquid. So particles are far apart, lots of energy. If you cool it down, they start to come back together, right? Because you're losing energy. And if you have a liquid and you continue to lose more energy, then the particles will get even closer and they'll stop moving. They'll just vibrate as a solid. So losing energy, the particles' entropy decreases and they get close together. And if you add energy, they get further apart and start moving faster. Which one is exo? Which one is endo? 3. Adding energy to a solid to melt it, let's say, or taking energy away from a liquid to freeze it. Which one's exothermic? Which one's endothermic? Right. So if we're melting a solid, we're going solid to liquid, we have to give this energy, right? Give it a bunch of energy so that the particles can melt. So that would be, what was that again? Endothermic, right. But if we're going from a liquid to a solid, exo, right, the liquid has to give off energy, get colder, lose all of its energy to form the solid. So freezing would be exothermic. Good. 28, we just kind of did. Melting is when a solid turns to a liquid by absorbing energy. Freezing is when a liquid turns to a solid by getting rid of energy, right? So that would be the exothermic process. What's a normal boiling or normal melting, normal freezing? What's that mean? Normal melting point. At standard pressure, right? So they don't say normal. I was just throwing that out there. 29. Deposition and sublimation. Deposition, Shelby.
Deposition is the change of a gas directly to a solid, and sublimation is a liquid or a solid breaking down.
From a solid to a gas, right? Deposition is gas to solid. Sublimation is solid to gas. Compare and contrast sublimation and evaporation. Sublimation and evaporation are both similar because you're breaking forces. To go from a solid to a gas for sublimation, liquid to gas for evaporation, they're breaking forces. But the difference between the two is subliming, you're actually, it's a stronger, I don't want to say stronger, there's more energy involved because you're skipping the liquid phase. Whereas evaporation, you're just going from liquid to gas. There's actually less energy needed for that. 30, that was it? Oh, that was it. Okay, so 435. 77. All right, define the term melting point, kind of did already. That's the temperature at which a solid turns to a liquid. Normal melting point, the temperature at which a solid turns to a liquid at standard pressure. 80. Evan, what do you think? What's that? That's a tough one. Tough? Go ahead.
I said the pressure, if you decrease the pressure, the snow will go directly from solid to gas.
Good job. But let's say this winter and there's going to be snow. There's a pile of snow on that little roof over there. Sometimes I see that little pile kind of get smaller, but I don't ever see any liquid water. What happens? The air pressure didn't change. So you're right, but let's say the air pressure can change. Yeah, that's it. Snow sublimes. That's it. Snow sublimes. The sun hits the snow, and the sunlight, the sun rays hitting the snow gives it enough energy to actually sublime. So it happens in the freezer too. If you get the frost around the outside of your freezer, maybe the top sometimes, maybe older freezers, that's because inside there's a little bit of sublimation going on. So like if you have ice or something that's frozen, it sublimes, the water vapor is solid, right? It sublimes and it redeposits on the sides and up top. That's what's happening. So that was 80. And 439, number 13. Zach's gonna give us this one.
I said A.
All right, why?
Because there's no energy.
So solid phase come in definite shape and volume because are not in constant motion. It's not a bad answer, but there's a better one. This is one of those tough questions where there's like a more right answer.
Yeah. Could be C.
Could be. You're getting closer. A was farther away. C was very close. D, yeah. Held together with strong forces, meaning the particles don't move. And that's, like I said, his answer A isn't a bad answer, but the real reason is D. Because of the strong forces, solid particles don't move around. They have a constant, definite shape and volume. So that D was like the best one. That was kind of a tough question. All right. Close those.
What happened to his textbook? It's like,
Oh, you grabbed the squirrely one.
yeah.
Leave that over to the side. I gotta get rid of that.
Okay.
Nice.
Burn it.
Okay, take out your notes. You should have table I out as well. Both of those things. All right. Go to table I, please. So notes in table I.
So it's a 6, right?
All day.
What?
All day.
What time does the day end?
11:59.
Or 12 o'clock.
Isn't that technically the start of the new day?
I don't know, is 12:01 start of the new day?
That's a good point. I'm not sure. I think 12 exactly starts
Can
the
we
new
look it
day.
up real quick?
But I don't know.
Yeah, 12 exactly because it's AM.
Right. Yeah, there you go. There's the answer. That's the thing. So 11:59, 59.
Sure? Yeah.
Feel pretty good about it.
Yeah,
Well, it has nothing to do with what we're learning, so let's move on. So, table I. Look at table I, and who's it going to be? Kayla, read the title, please. Oh, Kayla, we assumed, we discussed whether you did your homework or not, and we decided you were honorable, that you probably did it. Yeah, good. So I gave you credit. Heats of reaction, I was going to have her read this, but I'll come back to Kayla. Table I says heats of reaction at 101.3 kPa and 298 K. 101.3 kPa is what? Standard pressure. We say that so many times, you just have to memorize it at this point, I would think. That's standard pressure. What about 298K?
It's not.
Not standard temp. Standard temp is 273. Little confusing. Here's the difference. In chemistry, there's two scenarios. There's standard conditions and normal conditions. Normal conditions is this, 298. That's more like this room. 298 is 25 Celsius. It's a little warm. This room's probably like 20 Celsius, 21 maybe. 22. It's 22 Celsius in here, but 25 is closer to normal conditions. So that's what this table, all these reactions that you see listed, that's what the conditions are. So why am I showing you this table? Well, it relates to the demos from yesterday. By the way, who remembers which one was endo? Raise your hands. Which one was exothermic from yesterday? So you had the two white solids that I was kind of swirling around and everybody felt the bottom. And then I had the black stuff growing out of the beaker that everybody thought was so interesting. Which one was endothermic, which means absorbing heat? Which one was exothermic, releasing heat? Hold on, everybody think for at least 10, 15 seconds here. Which one was which? I'm going to actually write both reactions down today and explain that, and then we're going to learn how to use table I. Go ahead.
What?
You have your hand raised. Go ahead.
Alright, so the snowball stuff,
The white solids, yep.
I think that was endothermic.
Okay.
But I could be wrong.
Why?
Well, because like
What's endothermic mean?
to like take energy, keep energy. So
Gain energy, right. Absorb energy.
Well, it got cold.
It got cold, so did it gain energy?
Yeah, cold. No, you know what? It's exothermic is the correct one because it got cold. Was that right?
What does exothermic mean?
To put confusing me, man. Put it back out there. You know,
To give off energy, right?
off energy,
So
yeah.
did that thing give off energy?
Yeah.
Okay, where'd it go?
Yes. I don't know. I don't know what's right. I don't know if I was right the first time. I don't know if I'm right now.
Hey, we talked about it a little bit, but we didn't really fully explain it. Okay, well that's good. Maybe you confused everybody. We'll find out.
Endo and then the second one.
Which
is
one?
exo.
The white one was endothermic?
It's endo, the first one. Exo.
Why?
Because it is cold, so it was taking heat from our hand.
So if we touch it, it takes heat from our hand.
Man, see, you're confusing me. If you were just like, yes,
All I
yes,
asked
could've
was,
told you
I
yes.
didn't say anything. I just was like
Exactly.
asking.
You, that's the thing. You didn't say anything, so you made me think I was wrong.
That's what teachers do.
Correct. You said, well, God, no.
So the correct answer, so we're not confused anymore, is what Kristen said and what you said first. The white solids, when it touched our hand, it felt cold to us because our heat was going into it. Right? We learned that early in the year. Heat moves from, or energy moves from hot to cold. So anything we touch that feels cold to us is absorbing our energy, therefore it's endothermic. Anything we touch that feels hot to us is giving us energy. So that, I didn't really want you guys touching it, that's why I had the thermometer probe in there and had the iPad and you saw it went up 10 degrees or something. So that the black carbon that was coming out, that was giving off lots of heat, that was exothermic. How'd you know it was giving off heat? One, you could have felt it. I didn't watch you, it would have felt hot, but what was the other proof? Yeah, usually things with smoke or steam are getting hot, but the data was the temperature. The temperature went up in the water. So you had that reaction, and then I had around it water, right? The water was around it, and the water got hot, proving it was giving off energy. So what am I trying to get you to understand? The difference between endo and exo. Endothermic absorbs energy. Exothermic releases it. If you can memorize that, that's great, but then be able to explain it, that's even better. So what we're going to do is we're going to write those definitions down, and then we're going to relate it to table I. So I want to talk about table I a little bit now before we write those definitions. So if you look at table I, and you look over on the right side of the chart up on the top, kind of the heading, it says delta H, and then parentheses KJ, a little asterisk or a little star. Does anyone know what delta H stands for? Want to take a guess?
Sounds like a frat house.
A little bit. What's delta mean?
D.
What?
What? Delta is long triangle.
It's change.
Change. Delta means change. But you're right.
Is it
Lowercase.
military?
Triangle.
Yes, you're right. Yes.
Bravo, Charlie Delta.
Yes.
Charlie would know that. Charlie's military, man. Isn't that right? What's Z, Charlie? Zulu?
Zulu. Can we stop? Back to this. Are you looking at table I?
Actually, I am.
Good. The little triangle. It's a delta symbol. You said actually like it's surprising. I asked you to look at it. You should be looking at it.
Yeah, I know.
So the little triangle is change in. Change in what? What's H? What have we been talking about?
Changing. You know,
What's the title of the table?
heat reaction.
So what's H stand for? Heat. Delta H stands for change in heat. Look at that first reaction. CH4 plus 2O2 yields CO2 plus 2H2O. Yeah, that might be confusing, but that's kind of irrelevant. Don't worry about figuring out what that reaction is all about. Look at the energy, the heat, over on the right side. It says negative 890.4. That reaction I did yesterday with the thermometer in it, we could actually calculate the delta H of that reaction and have it similar to like this chart. We could actually figure it out. Next week we're going to do that. I'm going to teach you how to figure out energy changes in a reaction. This chart charts a bunch of them for us. You don't have to figure it out. You don't have to do it. It's already figured out for us. So this first reaction releases 890.4 kilojoules of heat. I know it releases it, one, because I'm a chemistry teacher, but two, I know how to read table I. How do I know that first reaction, negative 890.4, is releasing energy? If you're looking at table I, you should be able to figure it out.
It's losing heat. Because it's losing heat, right? Because that's what that negative means.
Yeah, but how do you know that?
Because the H stands for heat. Is that means the heat?
Because a negative is below zero.
All the things you're saying are pretty good, but there's an even more obvious way to read this chart. I think Kristen had already figured it out.
Oh, wait, no.
No?
I was
Okay.
just going to say that it's negative.
All right, yeah, negative means it released it, but
I was going to say the bottom.
everyone look at the very bottom, very bottom. A minus sign indicates an exothermic reaction. So you don't really have to memorize that. You don't really have to memorize that. So if you see a negative sign in front of a delta H value, what does value mean? A number? That means it's exothermic, releasing it. Guess what a positive number means? Endo, you're gaining it. So I want you to keep moving down table I until you see the number positive 182.6. Find 182.6, plus 182.6. So that reaction, the N2 plus O2 yields 2NO. That reaction is endothermic. How do I know? Because it's plus 182.6. Guess which reaction would feel cold to us?
This one.
That one, very good. Okay, that would feel cold to us because it takes in heat. It takes in energy. The first reaction is actually a combustion reaction. That would produce a lot of heat and you would feel it, okay, like burning a piece of paper, okay? It produces energy. So that's how this relates to exo and endo, and we're gonna do one more thing today. We'll get to that in a second. So leave that out, but in our notes, let's write this down. Exothermic process. So exothermic process, and this can go for, or this works, or I'm not wording that right. This applies. This applies to both physical and chemical changes. Physical and chemical changes. So if I dissolve salt in water, that's a physical change, but you know what? The temperature of the water could change if I dissolve salt in it. You may not know that, but it can. So that's a physical example. Those two demos I showed yesterday are chemical changes. Both can have energy changes. One can be exo, one can be endo. It just depends on the scenario. So both physical and chemical changes can be exothermic. Exothermic means energy is released. Energy is released. I thought I had a better one here.
The video, something popped up.
Something popped up on it. Edwin, what'd you do?
Slow battery.
All right, well,
Yeah,
I guess we'll see. We'll see if it lasts.
I get super long cord.
So where am I here? Oh, energy is released. So yeah, exothermic means we're getting rid of energy. I'm not going to write down usually it's hot because I don't want to confuse you when we talk about melting ice or freezing water. If water is going from a liquid to a gas or a liquid to a solid, so freezing it, it's exothermic. That doesn't feel hot to us, right? But why is it exothermic? Because the water has to get rid of all of its energy to form a solid. So that's another physical example. So I'm not trying to confuse you, but I have to talk about all the different types of scenarios. So freezing is exothermic, but it's very different than that demo, which was exo because it got really hot. So as long as you think about the scenario, what is really happening to the energy, you should be all right. But the first step is memorizing this, okay, and this, right? Putting those two together, then applying it. So next thing here, table I. Parentheses here, negative delta H. So when I say exothermic,
You always capitalize the E.
Yeah, what the heck?
oh, that's weird. You know why? Because of the letter in the table is always capitalized. So I just I don't know. I just do it. That's weird. Table E, or table I. Table I, negative delta H. Now, you're going to learn one other thing next week. Underneath this, I want you to write or negative Q. If you had lab today, it makes more sense to you. And Q, negative Q, is in a heat formula. I'm going to show you that right now, but it's not going to make any sense until you have lab next week or in class next week. We talk about it too, on Tuesday probably. So all of this relates to exothermic. Releasing energy, negative delta H, negative Q. I'll show you that in a second. But again, table I, we're focusing on that today. Negative means it's releasing energy. Flip the reference table on the back, all the way in the back. Find the heat formulas. Isla, read them to me, please.
Q equals MC delta T.
Good.
Q equals MF.
So Q equals MHF, yep. Yep.
And Q equals MH.
Yeah, Q equals MHV. All three have Q equals, Q equals, Q equals. What's Q stand for? Look at the little key there. Heat. So as far as you're concerned, delta H means heat, change in heat. and Q means heat. So it's two different tables, table I, and then the back has some equations. So we're going to learn how to kind of use both of those and relate it to exothermic and endothermic. All right, so I'm just showing you that, and that's where that comes from. We're going to deal with it next week. But again, this is what we're focusing on today. Negative means exothermic. All right, so endothermic is the opposite. So endothermic process. Endothermic process. This is where energy is absorbed or gained, whatever makes sense to you. And I'm not writing for physical and chemical. Again, it also applies though. It also applies to physical and chemical. So whatever. Endothermic can be a physical process like melting would absorb energy, or a chemical like the one I showed you yesterday. On table table I, holy cow. Table I, positive delta H, right? And then the heat formula, we have a positive Q. So these are things I need you to essentially memorize, but also associate. If you see a positive energy value, you should think endothermic. Positive Q, endothermic. What does that mean? Energy is absorbed, energy is gained. Okay, so now what we're going to do, I'm going to write down both reactions that occurred in the demos yesterday, and I'm going to show you how to use table I in, let's see, not how to use it, how to use table I in certain questions you might see on a test or a regents. Okay? All right, so we good? Move on. Yes, we look good. Okay. All right, so I'm going to write both reactions from yesterday. The first one I cannot remember because there's a lot going on. But the first one with the two white solids mixing. Here we go. So we had barium hydroxide solid. We reacted it with ammonium chloride solid. Need two of those. Arrow. We got barium chloride solid plus ammonia. That was the stuff that smelled like smelling salts, and the water. There was water in there too. So that was the two white solids mixed. That's what happened. That was the chemical reaction. You have your reactants and then your products. Underneath it, maybe leave a space. Oh no, that's the other one. What was the other reaction involving? Sugar and what?
Water, right?
Little bit of water.
It's sulfuric acid.
Yeah, sulfuric acid. So we had sugar, C12H22O11, that's our sugar, plus H2SO4, that's our sulfuric acid. And then the two products were steam, that's water, and what was the black thing?
Carbon.
Just carbon. So carbon solid plus water, H2O gas, and I think this is 12, I don't know, what's the other one, like 18 or something like that, 11. Doesn't seem to be perfectly
I have
balanced.
a question.
Hold on one second.
Yeah.
So this first one here, that was our endothermic, right? So that was endothermic. That was the white solids being mixed, and then this was the exothermic. All right, go ahead, Ryan.
So for like sulfuric acid, is that made in nature, or is it made in like a lab?
It can be found in nature.
Like how?
Caves. I know there's caves in the Southwest, I believe. I think I saw it on one of those like Planet Earth shows, where based on the minerals that are in the walls of the cave, when there's condensation, and it like mixes with or drips off the minerals or kind of dissolves them, perhaps there are little pools of. I think it's acid. I think it's sulfuric acid. That's just an example, but it can be if the right conditions are mixed. Well, it depends. You need some sulfur, obviously. That's sulfate. You need some water usually to to get the hydrogen from it. So, yeah, it can. Alright, so here's endothermic, here's exothermic. So, what I'm about to write on the board now is what you're going to be doing with table I, so pay attention. Go ahead and copy that down. So I put the delta H over here on the left side for that first reaction. I put the delta H, the heat, over here on the product side, the right side, for the second one. So, based on what I just did, I'm going to write two random reactions from table I on the board. You're going to write them down. You're going to take the value of delta H. What's value mean? The number. You're going to take the number, and you're going to write it in the equation in the appropriate spot based on what you just saw. If you're confused, that's okay. That means you learned something. Want me to repeat the directions?
Yeah.
Okay. So I put this delta H here on purpose. I put this delta H here on purpose. Why? Because of the type of reactions that they are. So I'm going to take two reactions from table I, write them down. You guys are going to take the value of delta H, so the actual number, and you're going to write it in the equation according to the type of reaction that it is. So in other words, you have to put the delta H, the value, on the correct side.
On those ones? Or the ones that are right
The
there?
ones I'm going to write down.
Oh, okay.
No, these aren't in here.
I think I got it.
You're using these for an example, that's all. Here we go. So I'm going to pick two. All right, so N2 plus 3H2 yields 2NH3 gas, gas, gas. And if you use pen, I guess that's just tough luck if you screw up. I want you to actually attempt this. I'm going to walk around and check. So I want to see how you're doing. And the other one here we'll do. Okay. So there's your two reactions.
So we just plug it in there, okay? That's how we should go.
Yep. I think I know what you're asking. Write down the value of the delta H, where it should go based on each reaction type. So you're going to have to figure out which one's exothermic, which one's endothermic first. Then look at the example I did with you and relate it to this. So you're applying. Hopefully you learn something, then you apply it to a different scenario, right? That's what school is all about. Well, that's what I use this example. That's hard to see. It's hard to relate this to this. It's kind of hard. I can see it. I understand, but you can't.
Is that better?
Which one's exo? Which one's endo? Okay. And this one's exo, right? So once you figure out which one is which, you do the same thing.
Oh, okay.
So based on the examples I gave you,
I see, I get it.
you figure out which reaction is exo, which is endo, and you do the same thing I did with the demos. In other words, put the delta H on the correct side based on, how do you know that? You did something that no one's done yet. Bree's ruining all my fun.
I just changed my answer.
good. It's a good thing. Brandon, what'd you do? So here's what I was trying to. So this is what I was trying to get you to, without me just telling you, is that anytime you have an exothermic reaction, the value of delta H, the heat, should go on what side of the arrow? The right side. Exothermic should always go over on the product side. Endothermic, we always write it on the reactant side. Why do we do this? Because the chart just gives us the value. If we want to write it in an actual formal equation, you have to put the heat somewhere to show that the heat is being released or absorbed. So if it's being released, it always goes on the right. Exothermic goes on the right with the products. The way I've always remembered that, even from when I was in school, I do remember this, is exothermic sounds like exiting. You exit at the end, right? Think of class. You enter in the beginning, you exit at the end. And you can use different analogies however you want, but I think of exiting as at the end of something. So at the end of the reaction, the products, it's all over, so the heat is exiting with it. So the heat that is lost, is exiting, is always with the products, always on the right. Does that make sense to me? Hopefully it makes sense to you too. Where we enter is endo. That's the beginning, the entrance, the front, the first thing you do, whatever's going to help you. The reactants, that's the beginning. So the reactants gain that endothermic energy on the left side. So you need that endothermic energy over here on the reactant side. Another way to think of it, the exothermic reactions only can give that off after they've reacted. That's the only way it can work. They react, then they release. Whereas endothermic, they cannot start unless they get their energy. So endothermic has to get the energy first, or it'll never react. These are things you didn't know. This is why I'm telling you. Anyways, however you want to do it, memorize it, understand it. I always want you to understand it. But if you at very minimum memorize it, that's good for a multiple choice question. But if you ever ask to explain it, which I will make you, you're going to be kind of screwed with that one. So try and understand the concept here. So anyways, this one is what? Exo or endo? The first one.
Endo, right?
I don't know.
Endo. I'm sticking with my gut.
Okay, why?
Because it,
Look at table I.
energy is like, I don't know how to explain it.
Look at the value of delta H.
Yeah.
What is it? Read it out loud.
Value, negative 91.8.
Good. Look at the very bottom of the chart. Good. It's exothermic, right? Why? Because it's a negative sign in front of it. It means it's releasing it. So this is what Bree did. Good job, Bree. What did I not put there?
A negative sign?
Right. The only weird rule here in chemistry is we don't put minus signs in equations. So this is the hardest part for students. You still got a couple minutes, so stay with me, stay focused. This is really a negative number for the chart, but we just don't show it. So anytime you see numbers on the right side, it's exothermic, and that means it actually does have a negative number for its value, but in the equation we don't show it. There's no easy way to teach that. Yeah, it is kind of weird, but that's the way it is. This one's easier. This is endothermic because it's positive, so it goes here. So what is that, 52.4? 52.4 kilojoules goes on the reactant side because it's endothermic. This is what your homework's on, practicing doing exactly this.
Hey, that's true, but did you see how